Good morning, 6th grade. Welcome to science class. This is week 5 and our last week together to go over our standard 6.1. I'm Jacqueline Adams from Denton Magnet School, and we're going to start today by kind of recapping everything that we've looked at. And let me start by saying, wow, we have covered a lot of information. This makes like 5 weeks of information that we're squeezing into 20-minute segments. So you guys that are hanging in there and meeting with me every week and going through this stuff, my hat's off to you. I'm proud of you for the work that you're doing. And let's just kind of take a minute to go over, kind of review everything that we've looked at so far. So first, let's just kind of talk about our standard. You know, 6th grade has been different this quarter because we only have one standard. Most of your other classes are covering 3 standards this quarter. But this standard is so large that we could chunk it up into 5 big pieces. But ultimately, the main thing is I want you to remember that this standard is all about modeling the sun, the earth, and the moon system. Now, once we understand those models, we can then look at causation for different phenomena on Earth. So specifically, let's look at kind of what we've done each week. So week 1, we talked about seasons. We started this by just looking at really the sun and the earth system. You know, how does that system interact and what are the big points? And mainly the big idea here was the causation of seasons. That we have different seasons on different places on Earth at different times because of the amount of direct sunlight. Well, what causes there to be different amounts of sunlight has to do with the 23.5-degree tilt of the Earth on its axis. It's this tilt that causes the sun's sunlight rays to come in at different angles. And so that heats the Earth differently and causes the different seasons. So that was the big idea from week 1. Then week 2, we kind of just went straight to looking at some models. We looked at the size model and we learned that the moon is 1/4 the size of the Earth and that it has 1/6 of the gravity. We're going to talk about gravity later today in this episode, so I want to stop for a minute and say, you know, a lot of students think that the moon doesn't have any gravity, and we learned that that's just not true. Everything has gravity. If it's made of mass, it has gravity. What do you think is holding those particles together? Gravity. So the moon does have gravity, just not as much as what's on Earth. That's why when you think of like any images you've seen of the lunar landings when we went to the moon, those guys were like running and kind of jumping on the moon because there is gravity. It pulls them back down, just not as much as Earth. It's 1/6. Then we looked at the moon's orbit, and we learned that the moon's orbit around the Earth is elliptical, meaning it's not a perfect circle. The elliptical orbit is oval-shaped, meaning there are points that are further away and points that are closer. And we learned that this causes apogee and perigee with the moon phases. And just meaning that sometimes the moon appears to be bigger and sometimes the moon appears to be smaller. So the moon's orbit is elliptical, and the moon's orbit and its rotation, remember rotation is just spinning, so the moon is spinning on its axis, but that spin takes about the same amount of time as its orbit. We call that synchronous. So the moon's orbit is tilted, it's oval-shaped or elliptical, and it is about the same time as its rotation, about 28 days. And then we also looked at a distance model and saw that the distance between the Earth and the moon is really much farther than we thought. It's actually 9.5 times the distance at the equator. Then the next week we started looking at phases of the moon. Big ideas from phases of the moon. The first one is the moon does not produce its own light. Like, what is the moon? It's a big piece of space rock. It's just rock that's orbiting the Earth. It does not produce its own light, but it's always half lit by the light from the sun. Half of the moon is always lit because half of the moon is always going to face the sun. We see the different phases of the moon based on how much of the lit half we can see. And ultimately we learned that if the moon is waxing, that means that the lit portion that we see is appearing to get larger. Meaning maybe we started with a new moon and then we see the tiny crescent, then we have a quarter moon, then we have a gibbous moon, then we're at full moon. That moon series was waxing. If you're looking at pictures of the moon, or if you're going out at night and you're looking up at the moon and you're trying to think about what you learned in science this quarter, you can know if the moon is waxing or waning based on which half is lit. If the right-hand portion of the moon is lit, we know that that's waxing. If the left-handed portion of the moon is lit, that's waning. Waning is the cycle of the moon where the lit portion is appearing to get smaller. So now starting at full moon position, we would then have a gibbous, which is just shy of a full moon. Then we would have quarter, then we would have crescent, then we'd back to a new moon. So the lit half appears to be getting smaller, that's waning, and that lit half will always be on the left. The way that I remember this is I think left, leaving, left starts with the L, leaving starts with the L. So that's just the way my brain likes to work. So I always know if it's on the left-hand side, the light is leaving, and that would be a waning. And then last week, we started on eclipses. Eclipses are all about shadows. And whether or not it's a solar eclipse or a lunar eclipse is about what shadow we're talking about. One thing that my students had a lot of questions about this week was about why we don't have eclipses every month. If a solar eclipse happens in the new moon position, and by new moon position we mean, okay, the sun is over here, then we have the moon, then we have the earth. Sun, moon, earth is new moon position. A solar eclipse can only happen in that position. When you're on Earth viewing a solar eclipse, it happens during the day. And you'll actually be looking at the sun. You'll be looking at the sun that's being covered up by the moon. Like, think about it. If you place yourself here on Earth and you're looking at the moon here and the sun is behind it, a solar eclipse, you're actually looking at the sun. You're standing in the shadow. You're not looking at the shadow. You're in the shadow on Earth. The reason that solar eclipses are more rare than lunar eclipses is because the moon is smaller than the Earth. So its shadow is smaller. So that shadow of the moon on the Earth, the only people on Earth that get to see that solar eclipse have to be in that shadow. Nowhere else on Earth is going to see that eclipse. So sometimes solar eclipses happen, but they happen over the ocean. 3/4 of the Earth's surface is covered in water, so oftentimes solar eclipses happen over the ocean, and so no one gets to view them. Lunar eclipses, on the other hand, a lunar eclipse happens when the sun, the Earth, and the moon line up in full position. A lunar eclipse can only happen in full moon position. And in that case, the light from the sun coming from behind the Earth casts a shadow on the moon. In that case, what we're looking at, if we're standing on Earth, we're viewing the moon, and the moon is moving into Earth's shadow. So we'll watch the moon turn like a hazy red color. So, solar eclipses, new moon position, happen during the day, and you're viewing the eclipse from Earth, you're looking at the sun. Lunar eclipses are more common. There are a few every year, and you're viewing the moon. They happen at night, and it happens in full moon position. And then our bottom line here talks about the big idea about why we don't have eclipses every month. We don't have eclipses every month because of the angle of the tilt of the moon's orbit around the Earth. Sometimes the moon is not at the right angle. It's got to be in like that Goldilocks position. If the moon is too high, the shadow won't reach Earth. Or if it's too low, Earth's shadow won't cover it. So there are only a couple of positions in this orbit where the moon is in that ideal position to cast the shadow to cause an eclipse. So that's going to bring us to the new stuff today, where we're going to talk about everything has been about, with this model, what phenomena are caused on Earth. So now we want to look at Earth's water. One of the things that makes Earth so unique is that it's covered in liquid water. Earth has water in all three states, and that really makes it unique and a large reason of why we have life on Earth. But let's talk about what we know about water. So water is a liquid. So by meaning a liquid, we've got some water right here, and I've got some different shaped jars. So this is a very basic concept, but let's apply to what it means in the big scheme of Earth. So if I take the water out of this container and I pour it into this container, and I'll pour it into this container, let's talk about what's happening. Gravity is pulling the water from one container into the next when I pour it. And because these three containers are all shaped differently, the water takes a different shape when I pour it. When I pour it into this container, it's going to take the shape of that container. Gravity is going to pull it down. When I pour it into this neat, and I like this container, he's a nice shape. When I pour him in here, now it's going to take that shape. And it's because gravity's pulling on that water. Earth, 3/4 of our planet is covered in water. So what effect does the moon's gravity have on Earth's water systems? Let's talk about that. Let me move over here. I've got a water balloon here. I'm going to set him on the table. So right now, what we're looking at, this balloon full of water is resting on the table, and the bottom of it is flat. If I pull him off the table, gravity's going to pull that water down. You can see where gravity is pulling this balloon down. The weight of the water is pulling, and now the bottom of this balloon is not flat. It's coming down at an angle. The same is going to happen with Earth. The water on Earth is the same as the water in this balloon. Gravity's going to pull it. You should have learned third quarter a lot about gravity in Earth's space systems. And we know that everything has gravity. And in orbit, what locks something in orbit is a dynamic between two objects' gravity. So in this case, we're talking about the Earth and the moon. It's locked into orbit because of both of their gravity. Think about it. If the moon did not have any gravity, then the Earth would pull it into the Earth. There has to be a pullback to keep it in orbit. So there's a dynamic between these two objects' gravity. The moon is pulling back towards the Earth, and it's going to pull the water with it. So let's back up just a minute to something we talked about in our first episode. The Earth is rotating. It rotates about every 24 hours, causing day and night. The moon's gravity and Earth's rotation is what causes Earth's tides. Now let's clarify something real quick when we talk about tides, because most of us have been to the beach. We're down here in lower Alabama, right on the coastline, so we're very familiar with the waterways around here. When we're talking about tides, I'm not talking about how big the waves are. That's surf, and that's largely caused by wind. I'm not talking about how choppy the waves are. When you go to the beach and you're out there playing in the water, I'm not talking about how big the waves are. When we're talking about tides, we're talking about how far inland does the water come on land. And it's typically pretty consistent. So I want you to think for a minute about any time that you've been to a beach. And normally when you go to the beach, you walk out on the dry sand and you're trying to decide where to put your beach stuff. And at some point you're going to come to a marker in the sand where all of a sudden it's wet sand. So the sand was dry, the sand was dry, the sand was dry, and then all of a sudden the sand is wet and it's harder. If you go to the beach and there's like hardly any wet sand, you walk to the dry sand, dry sand, dry sand, and then all of a sudden there's wet sand and the water is right there. There's only this much wet sand. That's going to be high tide. If you go out to the beach and there's a whole bunch of wet sand, by the time you get to the line, because when you're standing at that line where the wet sand is, if you look this way and you look that way, it's going to be pretty consistent all the way down the beach on where that wet sand is. If you go out to the beach and when you get to that wet sand, there's a bunch of wet sand, that's low tide. And that area of wet sand is underwater part of the time. When high tide comes in, water is going to cover that area. And then when the tide moves out and it moves back to low tide, then that area is not covered in water. So that's kind of what tide looks like. But let's talk about what causes it. So the dynamic we're looking at in this model is the moon's gravity and Earth's rotation. So we're talking about a 24-hour period. In a 24-hour period, the side of the Earth facing the moon is going to be at high tide. But this Earth is rotating. So as it rotates, the part of the Earth that is facing the moon is changing. And it's this side, it's these two sides that are going to experience high tide. The dynamic is it pulls the water towards it, and you end up with a bulge of water on the side facing the moon, and then also a bulge of water on the back side. So these two positions would be high tide, and then your perpendicular positions would be low tide. So as the Earth rotates, these different places slowly experience high tide. So how many tides does the Earth experience any given place during any 24-hour period? Let's think about it. This is easy to figure out. If it takes 24 hours for the Earth to rotate, and at this given point in time, we've got 2 high tides, and we've got 2 low tides, that's 4 a day. So for 24 hours, the tide is going to change every 6 hours. We have a high tide. The water reaches that closest position into the land where there's not a whole lot of wet sand. And once it reaches that highest point, then it starts drawing back. And in about 6 hours, it's going to be at that lowest point. And then it's going to start moving back up, and then it'll start moving back out. And that moving up and moving out is just the effect of the Earth rotating. So as the tide's moving out, it's because that place on Earth is moving away from the moon. So the water on Earth is absolutely affected and pulled by the moon. It's going to pull it towards it and away from it in these 2 positions, and then low tide in these positions. So every 6 hours it changes. Let me flip this real quick. So here are our big ideas for tides. That the gravity from the moon affects the water on Earth's surface. It has to. When we were pouring the water back and forth from these glasses, we indicated that, okay, water is a liquid, so it changes shape. It can be manipulated. And gravity is a force that can pull water. When we poured the water from glass to glass, it's gravity that's pulling that water down into the glass and spreading it out. We see that same dynamic on planet Earth. And then that the moon pulls the water to high tides as the earth rotates, causing a high tide every 12 hours. So every 12 hours there's a high tide. And think about it, in our model, it totally shows this. Because if this area is high tide in 12 hours, it's going to rotate half a rotation. And it's going to be at high tide again. And when it makes it back around again, that's 12 hours. Every half a rotation is 12 hours. So that's where our tides come from. So, guys, we're going to have to kind of start wrapping it up here. I just really want to tell you guys that as a district, I'm so proud to be part of Mobile County and what you guys are doing no matter what, whether you've been just watching these shows, whether you've been doing some digital learning online, whether you've been doing paper packets at home, the fact that you're doing it at all means that your education matters to you. I really want to encourage you guys that during the summer that you stay curious, find some things to wonder about and go learn about. Being the driver of your own education is a powerful force. I hope you guys really learned a lot about the sun, earth, moon. I hope that you're interested in science, and I hope that you guys have an excellent summer and that I will see some of your smiling faces in the fall. And I'm out of here, and I enjoyed the time together. Bye, guys.